Good morning, everyone. We're going to start with section 1.5. So I was going to write good morning, but section 1.5, which is limits involving infinity and asymptotes. See, it was fun to do the exercise that I just sent you by email. It shows a little bit about limits at infinity, so this infinite limits if you want, so limits that are revisited. So it's a good exercise. This one is different than this one. This one is x minus 2 and this one is x plus 2, and you notice for x minus 2 it's different. The answer is completely different, so please follow up very well. And here, if you notice, this is absolute value, and we agreed in the lessons that when we have absolute value we have to do less than and greater than 0, so that it makes sense. This is a piecewise function in disguise. And then when we want to approach minus 2, we approach it from the left and from the right by taking separate limits, one from the left and one from the right, and then they are not equal, so the limit does not exist. But what will I use? I will use the first example, the limit of absolute value of x minus 2 over x squared minus 4 as x approaches to minus 2. I want to use this example first to remind you that limits first you substitute. You do not assume that there's a problem before you really prove it there is a problem. So you substitute minus 2 by minus 2 over minus 2 squared minus 4. Absolute value, you do what is inside all together as a package, then the answer you do the absolute value for it. So minus 2 is minus 4. Absolute value of minus 4 is 4 over 4 minus 4, 0. We agreed from before, so this is just a reminder for you. We agreed from before that when we have a number over 0 and limits, of course, and limits, this means that the limit is plus or minus infinity. I put asterisk like this because it can be plus infinity from both sides, it can be minus infinity from both sides, it could be plus infinity on one side and minus infinity on the other. So what do I have to do when I'm asked to do a limit like this? We're supposed to check sided limits, and I told you last time, how do you check sided limits in a very fast way? You just take a number, one number. You do not need to do tables of values, you just need one number. Like over here you choose a number less than minus 2 is minus 2.1, and a number of 0.2001 if you want to be precise, and here minus 1.999. You take those two and you substitute them in the calculator to find out what the result is. You don't put the result, of course. These are just checking if I know the result is what. The result has to be infinity. All I'm checking is whether it's plus infinity or minus infinity, because I know when a number up there is divided by a very small number close to 0, then the answer will be either positively large or negatively large. So over here we take our calculator, we put minus 2.001 minus 2. It will always be a number close to 4, but you can do it. You can put absolute value minus 2.001 minus 2, all of it divided by bracket minus 2.001 squared minus 4. What is the answer? Minus 2 squared here. See, I forgot a bracket. See, this is all squared, so it becomes, I forgot to put a bracket. See how it makes a big problem? Because if you forget to put the bracket, the minus 2 here will not be squared to become positive, so you have to put a bracket. I saw there's something wrong because the answer didn't look like what I wanted it to be, so I knew that I input something wrong on the calculator. What did we get? We got a positive large number. This means that from this side it's plus infinity. Let's do the other side. Absolute value of minus 1.999 minus 2 divided by bracket minus 1.999 squared minus 4. So I got a minus of 1,000, which means the numbers are decreasing to minus infinity. This means that x equals minus 2 is a vertical asymptote. And this means that when we graph later on, at minus 2, we will see that we have a vertical asymptote here. At x equals minus 2, we have a vertical asymptote. And when we approach it from the left, the limit is plus infinity. And when we approach it from the right, the limit is minus infinity. So the function will look like this. It will have to go up here and it will have to go down there. So such an example comes from the simple example of a hyperbola. What's the limit of 1 over x as x approaches 0? The first thing I do is substitute. I get 1 over 0. Number over 0. What do you do? What are the steps you take? First, you put that the answer is plus or minus infinity and that x equals to 0 is a vertical asymptote. But then this is not enough, because this tells me that I have a vertical asymptote but does not describe the situation for me. And I want to know the exact situation. So what do I have to do? I have to take the limit from the left alone and the limit from the right alone, because I want to know if from the left I am going up to infinity or going down to minus infinity, and same for the right, because they have nothing to do with each other. So what do? I take a number very, very, very small, less than 0, yani it's negative. 1 over a negative 0.00001, it will become negative million, so negative infinity. 1 over a positive, it will become plus infinity. So the limit from the left is not equal to the limit from the right. They are not the same. If they were the same, I can say the limit as x approaches 0 is plus infinity, for example, or minus infinity. But because they are different, then this limit cannot be described except with the word does not exist. All right, so this is something that we have already learned. But as I told you last time when I was teaching it to you, I was telling you that we will revisit that again. So we've been saying vertical asymptote, and vertical asymptote over and over again. Vertical asymptotes, as we said, they are straight lines. It doesn't mean we don't, it's not about not crossing them. The idea is that as we approach that value, as we approach that x value, the limit of the neighbors either grow without bound to plus infinity or they grow without bound to minus infinity. So this is the idea. Likewise, the limit of 1 over x squared as x approaches 0 will be what? Will be a number over 0, 1 over 0. Again, if you remember, a number over 0, if I want to do tables of values, as x approaches 0 from the left, what will happen? If I'm minus 0.9, what will happen? Sorry, 0.1, very close to 0. Then minus 0.01, minus 0.01. What will happen when I square the number and then take the reciprocal, do 1 over x squared? What will happen? But these are becoming smaller and smaller and smaller, closer to 0. This means that when we take the reciprocal of that, what will we get? So when we do 1 over bracket minus 0.1 squared becomes 100. It grows. You're in the denominator is becoming smaller. This means the answer will become bigger. What will happen if we have 0.01? Oops. $10,000. What will happen if this becomes very, very, very small? So like we add 10 zeros. Do you imagine how big the number will be? It will be 1 with 18 zeros next to it. So see how big it is? That's the idea. So here it will be 1,000. Square 0.01 or 100, and here 10,000, and so on. So like, so we see it grows without bound to plus infinity. So it's a very important thing to know how to handle when dividing by 0. When we do limits, we are approaching 0. We're not exactly 0. So that's the idea. That's the trick when we are doing limits. Same if it was 0 plus, it wouldn't matter because the minus will be cancelled. But imagine we are squaring here. When you square, the minus and the plus will have the same answer. So the limit from both sides is plus infinity. So if I get the limit from the left it will be plus infinity, and the limit from the right is also plus infinity. See, because they are both plus infinity, the limit still does not exist. It's an infinite limit, so infinite limits do not exist. But because they are the same, I can say that the general limit around 0 is plus infinity. This means that when I come to drawing, this will be my vertical asymptote, x equals 0, and I will be heading to plus infinity from both sides. That's the trick about it. So this is good. There are so many examples where the sided limits do not agree, which means that we have, just as I did now. So if I look here, limit as x approaches 5 of 1 over x minus 5 cubed. What do? You directly substitute 1 over 5 minus 5, 0 cubed is 0. Number over 0, what do you directly say? It does not exist, which means x equals 5 is a vertical asymptote. Directly, when you know it's plus or minus infinity, what is your duty? Your duty is to separate the left from the right. And you know both answers are infinite. What is your job only is to decide whether it's plus or minus infinity. How do you do that? You take one value only, all right, because you already know the answer should be infinity, so you do not need a table of values and checking 3 different numbers and so on and checking the pattern. We know the answer will be infinity, but all we need is it plus infinity or minus infinity. So first, on the left, less than 5, like 4.999 minus 5, the whole thing cubed. Do you see how big the number is in the negative side? So this means that the numbers are becoming bigger and bigger all the way to minus infinity. Whereas 5 plus, so here what option did I use? 5 minus, I used the option 5.99. 5 plus, I will use the option 5.001. Look, it's a big number, but now it's positive. So it's plus infinity, not minus infinity. Since the limit from the left and the right, they do not share the sign, I cannot say that the limit here is infinity. What do I have to say? I have to say that this limit does not exist. All right, let's look at tan x. So this is in trigonometric functions now. Let's look at the limit as x approaches pi over 2 of tan x. Again, this is one of the limits that students do not remember, that they cannot look at it at one shot. How does tan x look like? Tan x is a function that has infinitely many discontinuities, right? So from minus pi over 2, it goes all the way up. Then it goes all the way up again. Before, it was going all the way up. It's an increasing function. This is x equals minus pi over 2, pi over 2. This is 3 pi over 2. You remember when we talked last time about how many discontinuities does tan x have? It has infinitely many discontinuities. One of those discontinuities is pi over 2. See, if I want the limit at pi over 2 of tan x, many of you will remember that pi over 2, oh my god, I know pi over 2 is a vertical asymptote. So directly, what do they put here? The answer is infinity. This is wrong. This is not right. This is a wrong statement, and students have it as a common mistake most of the time. So please make sure that you do not do this mistake over and over again. So what do we have to do? You tell me. I know that it's a vertical asymptote, but when I know it's a vertical asymptote, I know the limit can be plus or minus infinity. I cannot judge from both sides at the same time. What do I have to do when I know the limit, there is a vertical asymptote and the limit is infinite? I have to judge the left limit from one side and the right limit from another side. See, the limit of tan x when we approach pi over 2 from the left, this is pi over 2. When I approach pi over 2 from the left, where is the function values going? They are going all the way up to plus infinity. Whereas when I approach pi over 2 from the right, where are the function values going? The function values are going all the way to minus infinity. You see why saying this does not make any sense? Because this limit does not exist, and actually the limit from the left is different from the limit from the right. Similarly, when it comes to cotan x, and I want you to remember those two examples very carefully because many of you do the same mistakes. When it comes to limit of cotan x at 0, cotan x, this is x equals 0, x equals pi. It drops and so on. Right? This is cotan x. Because it drops, see the limit from the left of 0, as I approach 0 from the left, the function is going to minus infinity. As I approach 0 from the right, the function is going to plus infinity. See, it's dropping from plus infinity. So over here, this is very important. Similarly, if I do any pi minus, pi plus, they will react the same way. Because again, at pi minus, I'm going to minus infinity. Pi plus, I'm plus infinity. Actually, if you take any multiple of pi, any of those discontinuities, you will get the same result. And here, if you take any 3 pi over 2 minus 5 pi over 2 minus pi over 2 minus, all the discontinuities behave exactly the same way. From the left, they are something, and from the right, they are something else. So please make sure that you remember this very, very well. There's another thing that I want to cover in this section, which is limits at infinity. What we covered already are infinite limits. What we're covering now are limits at infinity. They are two different concepts. Limits at infinity is finding what happens as x grows to plus infinity or x grows to minus infinity. What does that mean? Let me explain to you. See, a function, for example, let's look at x squared. We put those arrows to say that it continues. So as x grows, here x will grow all the way, all the way, all the way. This arrow, what does it mean? It means it continues. So this will continue all the way to where? To plus infinity. Asking about limits at infinity, a limit like this of a function is like asking how is the function behaving when x grows to infinity or when x goes to minus infinity. So those are the tails of the function. The tails. We have two tails for the function only. That's why those are the only tails we ask about. What is happening when x goes to plus infinity and what's happening as x goes to minus infinity. So over here, if you notice, y equal x squared, the simple parabola, when x goes to plus infinity, what happens to the y values? They also grow all the way up to plus infinity. And here, when x goes to minus infinity, when this continues, how is this function behaving? It's growing and growing and growing and growing without bound, all the way to what? To plus infinity. Do you see how this is? Now, another example is the simple hyperbola again. But now I'm not studying around 0. I'm studying around plus infinity and minus infinity. So the hyperbola that you know, what happens to it as x grows very, very, very large and as x grows very, very, very small? So what is the pattern that the function is behaving as? So if you remember, the hyperbola looks like this. So I will show you graphically, then I will show you mathematically. The hyperbola looks like this. As x goes to plus infinity, and as the x values increase and increase and increase, what is happening to the y values? The y values, what's happening to them? They are decreasing all the way to how much? 0. But they never become 0 because 1 over x will never be equal to 0. But the limit means we are coming closer. We are not exactly equal. We are coming close to what number? To 0. Similarly, as x goes to minus infinity, what's happening to the function values? The function values are becoming smaller and smaller and smaller and smaller, which means they are approaching 0. This is called limits at infinity. They study how is the function behaving at the tails only. How is the function behaving when x becomes very, very large or when x becomes very, very small. If you want to also make sure that what I said is right, Take values that are becoming very, very big. So if I take x values and then check 1 over x. If I take 1,000,000, what does 1 over x become? To see that when x becomes bigger and bigger, what's happening to the function? 1 divided by 1,000,000 is 1 times 10 to the power minus 6, يعني 0.000 imagine. So over here, look how small this number is, and we're still at million. What if we continued all the way to plus infinity? This number will keep on becoming smaller and smaller and smaller, approaching zero. Approaching zero. It is never equal to zero. Try to solve 1 over x equal to 0. It can never be solved. But because we are studying limit, this is okay, because we are becoming almost 0. We're not exactly 0. These are very important. When you remember that the limit as x approaches plus infinity of 1 over x is 0, and the limit as x approaches minus infinity of 1 over x is 0, this helps us a lot in a lot of things. The first thing it helps us in is it helps us in finding or defining a new term, which is horizontal asymptote.